In this lecture, we want to look and see how to use the sun as a compass. So far, you've seen how to navigate by the sun without needing a watch. But if you have a watch, or any other timepiece for that matter, and if the sun's maximum altitude for the day, which occurs at land, does not exceed 45 degrees, the sun can act as your giant celestial compass for the whole day, except for perhaps in the very early morning and the very late afternoon. At those times, just trace the sun to the horizon and get the bearing that way. Here's how it works. The sun moves across the sky at 15 degrees per hour. There are, after all, 360 degrees in a circle, and there are 24 hours in a day. So 360 degrees divided by 24 hours equals 15 degrees per hour. You can see here the sun moves at 15 degrees an hour across the sky. And when the sun's maximum altitude for any given day is 45 degrees or less, its horizon bearing change is close enough to 15 degrees per hour to make the sun useful as a compass as long as you have a watch. So let's say it's 10:30 and the sun bears, let's call it 135 degrees. At 11:30, it would bear 150 degrees. At 12:30, 165 degrees, and at 1:30, 180 degrees, and so on. So you can look at your watch and add 15 degrees per hour, and you pretty much can get the sun's bearing at any given time. But this only works when the sun reaches a maximum height of, say, 45 degrees, somewhere around in there, 45 degrees. When it's higher than 45 degrees, the relationship of the sun's movement across the sky to its bearing as projected down to the earth is not a good one, and you can't use it. So this would be used, let's say, in the wintertime when the sun is relatively low in the sky in most places, or any time that the sun is low in the sky. Way up north, the sun hardly ever gets high in the sky, so as long as the maximum altitude for the day is not higher than 45 degrees, if you can get the bearing of the sun at any particular time, then you can just look at your watch and add 15 degrees per hour and pretty much know the bearing of the sun at that time. If you're not sure of the sun's maximum altitude for any given day, around noontime, around solar noon, just poke a straight stick into the ground and look at the sun's shadow. If the shadow is longer than the stick, that means the sun is less than 45 degrees of altitude. But if the stick's shadow is shorter than the stick, that means the sun is higher than 45 degrees. There's nothing, you don't have to be exact about the 45 degrees. That's just sort of a good guess mark. If it's 46 degrees, I don't know if it would make a world of difference, but somewhere around 45 degrees, the whole relationship of bearing as projected down to the horizon and movement across the sky of the sun breaks down. So just because the sun moves across the sky at 15 degrees per hour does not mean that the sun's bearing as projected down to the horizon necessarily moves by that same amount, by 15 degrees per hour. The sun's movement across the sky and its hourly bearing change can be quite different at those times when the sun passes high overhead. Let's look at an example. We'll say you're at the equator and it's the day of the vernal equinox. On this day, in this location, the sun will rise at 90 degrees, move due west across the sky, pass straight overhead, and continue due west until it finally sets at 270 degrees. All morning long, the sun will move through the sky at 15 degrees per hour. But all morning long, it will also bear 90 degrees. Then at land, its bearing will instantaneously change from 90 degrees to 270 degrees. The sun will then bear 270 degrees for the rest of the afternoon until it sets in the same direction. Okay, looking at that extreme example, you saw that the sun moved across the sky at 15 degrees per hour, but all morning long it bared 90 degrees. And then it had an instantaneous 180 degree change at high noon at land. So in that extreme example, there was no way that you could relate the sun's movement across the sky at 15 degrees per hour to its bearing as projected down to the horizon. And the reason is because the sun is very, very high in the sky. And when the sun is very, very high in the sky, the bearing change as projected down to the horizon bears little, if any, resemblance to its 15 degree per hour movement across the sky. Let's look at another example of what I'm talking about here. In this illustration, if you see up here at the very top, this is your zenith. The zenith is the point that's straight overhead from you. So in this case, the sun is passing very close to the zenith. It's very high in the sky. And of course, it moves at 15 degrees per hour, but a little movement up here, way high in the sky, translates to a lot of movement down here on the ground. So the sun moves just this little bit right here between these two depictions of the sun, but its bearing as projected down to the horizon spans this whole distance here between, say, 135 and 180 degrees. So a little movement high up translates to a lot of movement down at the ground. And so you can see in this illustration here, when the sun's altitude its maximum altitude for the day, that's its altitude at local apparent noon or land, when the sun's altitude is less than about 45 degrees, its 15 degree per hour sky movement relates closely to its bearing change as that bearing is projected down to the horizon, meaning that you can correspond the passage of time with the movement of the sun. So every hour you can just advance the sun 15 degrees. And so you can, if you know the bearing of the sun at any one time of the day, from then on out for the rest of the day, you just have to look at your watch to compute the approximate bearing of the sun. You may at some point have run across a watch method for finding direction from the sun. This watch method only works when the sun's maximum altitude is 45 degrees or less. So when the sun's maximum altitude for the day is higher than 45 degrees, the watch method doesn't work too well. So you want to at least be aware of that. After watching these videos on the workings of the sun, you now know how to trace both the morning and the afternoon sun back to the horizon to find the direction of sunrise and sunset, and the bearing for which you can estimate using the date and the sun's maximum amplitude at your latitude, a value that, by the way, is now tucked away in your memory. Being able to determine the spot where the sun rose and later in the day the spot where it will set using the tracing methods that we've talked about, coupled with the ability to estimate the bearing for each of these spots, allows you to use your hand as a makeshift protractor to measure from the known bearing of sunrise or sunset location to find the sun's current bearing. To get directions at midday, you now know how to use a shadow stick to determine an approximate east-west line to be used to find the sun's current bearing. You also know that at land the sun bears due south in the northern hemisphere and due north in the southern hemisphere. Provided you have a fairly accurate timepiece and you know the time of land, which is another good value to have tucked away in your memory, at least you'll know the sun's bearing at high noon. What's more, provided that the sun's maximum altitude for the day is no greater than 45 degrees, which you can use a stick to measure to find out, you know that the sun's bearing away from land will change close enough to 15 degrees per hour so that the sun and your timepiece can be used together to determine the sun's bearing all day, with the exception of the early morning and the late afternoon. And once you know the sun's current bearing, which you now know how to estimate, you have an effective guidepost to navigate for at least the next 20 or 30 minutes until the sun changes position so much that you have to rework the sun's bearing. This knowledge of the working of the sun, I'm sure, will prove useful to you. It has proven itself to be very useful to me as an outdoorsman, and I know it will be useful to you also. It's comforting when you're traveling across strange terrain to be able to look at the sun and pretty much tell which direction you're going by just looking at the sun. And if it corresponds with your compass, then that gives you that much greater confidence in your navigation. I hope you've enjoyed this video series on the workings of the sun, and I hope you get to put it to good use in the great outdoors. Thank you for joining me.